Okay, in this section, we will evaluate the controller design using the frequency response. Let's recall before this, I already explained to you how from the transfer function in the Laplace form can be converted into the frequency response form based on the amplitude ratio and the phase angle. Now we take a look on the application. How the frequency response can be applied as um, tools to measure the stability for closed loop system. In this case, we involve the controller. So, in the previous case, we use what we call it characteristic equation, where you have the 1 plus GP, GV, GC, GM equal to 0. Where this equation is used for the Roos stability criterion. Roos stability criterion. So you develop the Roos array, and then you put the coefficient on each row, then you classify it on the first column as long as it become greater than 0, must be positive. So if the first row become positive, then you will have a stable process. That one is based on the Roos stability. For the frequency response, we involve the input in the form of sinusoidal, the sinus wave. So how the stability can be evaluated? So in this case, we analyze based on the GOL. GOL stands for the transfer function for the open loop. OL is the open loop. Usually the GOL equal to GC multiply with the GV multiply with the GP multiply with the GM. So when you have all of these four transfer functions, that means it refers to the standard block diagram. So let's say if you have the GIP, the transducer, that means your GOL will be changed. GOL equal to GC, GV, GP, GM, GIP. Why we need to include the GIP? Because here we want to know the stability of the closed loop. Here, however, by using the frequency response, it called the GOL only because you don't have 1 plus. In this case, you have 1 plus. So that means one closed loop, and then what is the transfer function inside the loop? In this case, we still have the loop, but without the close. So that means the loop is not merged, it's not connected, but still we consider the transfer function. For the Roos stability, actually 1 plus GP, GV, GC, GM. Sometimes we call it 1 plus GOL equal to 0. So 1 plus GOL stands for the closed loop because we already close it by 1. But this one, it is called open loop only. We didn't consider the one here. But still the same thing, we want to measure the stability of the given transfer function. So in order to measure the stability, we use this following criteria known as the Bode stability criterion. Before this, you use the Roos stability, but in here we just use the Bode stability criterion. In this Bode stability criterion, we have what we call it gain and phase margins. So in the gain and phase margin, this means we will find the margins and we compare with the standard one. The guideline given, and then let's say you get the margin violating the guideline, then it become unstable. It's like that. What if your process become unstable? That means you need to retune your controller. That means your controller is not good enough. Change the controller. By changing the controller, you will have a new controller parameter. In this case, we will use what we call it Ziegler-Nichols tuning techniques to find new controller parameters. So by finding the new value, then we will evaluate again. The process becomes stable or not. That's how we can improve the process. So you have the transfer function, you have the GC, GV, GP, GM, and then you develop the border diagram, you calculate the margin. If the margin violating the range given in the guideline, then you need to find new controller parameter, Kc tau I tau D for example, by using Ziegler-Nichols technique. Once you find it, then do it again. The new border diagram, find the margin until the range is acceptable in accordance with the given guideline. Then you stop. So this is the way how the stability can be evaluated using frequency response. Okay, let's take a look what is meant by border stability criterion. Okay. In this criterion, it indicates that a closed loop system is unstable if the FR here stands for the frequency response, FR of the open loop, TF is the transfer function. If the GOL, GC, GP, GV, GM has an amplitude ratio greater than 1 at the critical frequency WC. Otherwise, the closed loop system is stable. So, meaning that this is our guideline. AROL at WCO must be equal to 1. Greater than 1, then it becomes unstable. Less than 1, it is stable. What is the WC? So sometimes here WCO, sometimes we call it WC. It's the same thing. Sometimes we call it critical frequency, sometimes we call it crossover frequency. But both are the same thing. Note, WC, value of WC where the open loop phase angle is negative 180. So this means the phase angle at negative 180 and then you reach the line, that is your WC, critical frequency. Then we need, here usually we combine. This one is only for the phase angle. We have the amplitude ratio diagram. So we need to combine both, then we can find the value of the AR. So here, this is the first criteria for the border stability. AROL at WC must be equal to 1. Greater than 1, unstable. WC occur at angle negative 180 degree. So let's take a look on the example. Let's consider the following transfer function where you have the third order. So that means in this case you have third order transfer function, but the tau is similar. It's fixed at 0.5. This is your GP. Let's recall for the criterion, the border stability criteria, you need to consider the GOL equal to GP, GV, GC, GM. So here you have the GP and the GV is given. GM is also given. And then if proportional controller is used, that means your GC equal to KC. So this is your transfer function for GC. In this case, the question asks you to determine the stability of this closed loop using three values of Kc, 1, 4, and 20. So we need to develop the GOL first. So that means the GP must be multiplied with the GV, multiplied with the GC, multiplied with the GM. So the solution, okay, you have the GOL, then this is your GOL. So that means 2 multiply with the 0.1, multiply with the 10, you get 2 again, and then you multiply with the Kc. For the first part, we didn't change the Kc value, still the same one. Okay, so based on this, you need to develop the amplitude ratio and the phase angle. So for the amplitude ratio, here will be 2 Kc, and then you have the square root. 0.5 square is 0.25 W square plus 1, and then power of 3, because you have 3 transfer function of 0.5s plus 1. And then for the angle, that means you will have a negative inverse tangent 0.5 W. So you have negative 3 inverse tangent 0.5 W because you have 3. So negative inverse tangent 0.5 W minus inverse tangent 0.5 W minus inverse tangent 0.5 W. So you have like this overall phase angle because you have the same tau. So this can be equivalent to this one, negative 3 multiplied with the inverse tangent 0.5 W. So now, based on this, we change the Kc value to 1, 4, and 20. So, based on the Bode stability criteria, it indicates that AROL at WC must be equal to 1. So, based on this, we develop the Bode diagram. So, you have the AROL and the phase angle degree. So, you have this following frequency. This will be included into AR in order to calculate the value of AR at which frequency. So in the end, you will have 3 different AROL and 1 angle. Why 1 angle? Because here, in the previous slide, in the phase angle expression, you don't have any Kc. So that means in the end, you change the value of the Kc, the angle still remain the same. But for the AR, the value of the AR will be different since the Kc value is changing from 1, 4 to 20. For AR, you have 3 graphs, and for the phase angle, you have 1 line only. So here the criteria AROL at WC must be equal to 1. AROL must be occur at WC. WC occur at negative 180. So this line, you need to draw until it reach this angle line. So from negative 180, you draw it until it reach the angle line. Then, based on this, you will have the value of WC. In this case, based on the log diagram, is 1, 2, 3, around 3. 4, 5, 6, 7, 8, 9, 10. It's not 1.1. Between 0.1 and 1, you increase by 0.1. For 1 to 10, you increase by 1. 10 to 100, you increase by 10. It's like that for the log graph. So here the WC is equal to 3. And then here you need to move your line until it intersect the next AR line. So this is your AR line for Kc equal to 1, Kc equal to 4, Kc equal to 20. So in this case, your AR for Kc equal to 1 is around here. So this means based on the previous, it show you 0.25. Here is around 1. Here is around between 1 to 10. Let's say 5. So in this case, it states that AR or L in bracket WC equal to 1. Greater than that, it becomes unstable. So for KC equal to 1, you have 0.25. The value of AR or L equal to 0.25. That means your process is stable when you use the KC equal to 1. If you use the KC equal to 4, the value of AR or L equal to 1. So that means it is on the border of stability. So we call it partially stable. This one stable. This one partially stable because it's on the line, on the border. But if we use the KC equal to 20, the value is 5, greater than 1. So the meaning that for the KC20, unstable system. Meaning that the closed loop response, if you use the KC equal to 20, become unstable. So no point to use this value. How about KC equal to 4? Can we use it? Actually, no, because it is partially stable. We want to have a completely or fully stable process. So that means must be less than 1. 0.99 is okay. But 1 is not okay. It's on the border. Either stable or not stable. So in this case, maybe for the 4, you cannot use it. Then it leaves you to KC equal to 1. So if you use KC equal to 1, the process become stable. This is based on the border stability criterion. Okay, let's take a look at another example. Now we have the GP equal to 4 exponent negative S over 5S plus 1, where the GV equal to 2, GM equal to 0.25, and GC equal to KC, proportional controller. Find WC. What is the maximum value of KC for a stable system? So in this case, the KC value is not given. We need to find it. But the GP, GV, GC, GM is available. So you can develop the GOL, GP, GV, GC, GM. So this means we have 4 exponent negative S over 5S plus 1 multiply with the 2, 0.25 multiply with the KC. So by multiplying 5 multiplied by 2 multiplied by 0.25, you will get 2. So this means your equation will be 2 KC exponent negative S over 5S plus 1. So in this case, we will develop the amplitude ratio and the angle. Let me erase this one first. So here the AR will be equal to 2 KC. Exponent negative S become 1 for the AR. 5S plus 1 become 5 square 25 W square plus 1. So this is your AR. And for the phase angle, you have 2 KC become 0 because it is the real number value. Exponent negative S become negative W. The theta is 1, so negative W only. And then you have the negative tangent, inverse tangent 5W. So this is the value, the expression for the amplitude ratio and the phase angle. So based on the border diagram, you have the frequency 0.01, 1, 0.01, 0.1, 1, 10, 100. So we substitute the value of W inside the equation in order to plot the border diagram. Okay, based on the transfer function, then we will, based on the amplitude ratio and the phase angle expression, by substituting the frequency 0.01, 0.1, 1, 10, and 100, we can plot the following graph. Okay, let's say we have this kind of graph, where the first one for the AROL and the phase angle. Okay, in the previous one, we know that the KC is not given. So let's say, in this case, we eliminate the KC first. So this means we can obtain the value of the AR. So in this case, the angle happened at the negative 180. So we start at here until we draw the line until it reach this, the angle line. Then we can have the WC at 1.69, and then by prolong the line until it reach the AR line, then we can have the AROL 0.235. So basic. Okay, based on the border plot, we can obtain the value of the WC from the graph, which is 1.69, and the AROL equal to 0.235. So the question asks you to find first the critical frequency, which is 1.69, and then the maximum KC value. So here maximum KC value can be found based on the page in the textbook, page 263, equation 1359, which is the KCU equal to 1 divided by AROL at WC. KCU here means the ultimate KC, or sometimes we call it the maximum KC. So ultimate or maximum. Ultimate KC, maximum KC. Ultimate KC value. The maximum KC value is the same thing in this case. So this means it show you the maximum value before it become unstable. So the formula is 1 divided by AROL at WC. This one is not multiplied. This means AROL at WC, which is 0.235. So the formula equal to 1 divided by 0.235, which is 4.255. So meaning that if we use this formula, then the process will be partially stable because it is on the border. Remember that AROL equal to 1, right? So AWC equal to 1. So in this case, if we use the KCU 4.255, the process is actually will reach AROL equal to 1. So it is become partially stable. So this is the maximum value you can use before it become unstable, although it is not preferable. Okay, before this we use the border stability criterion, where AROL at WC must be equal to 1. Other than more than 1, then it process become unstable. Another criteria that can be used to measure the stability is by using the gain and phase margin. So here the gain margin is let the ARC, amplitude ratio at critical frequency, WCO, and the corresponding phase angle is 180, where the gain margin formula is defined by GM equal to 1 ARC. So ARC here happen at WC. So 1 divided by ARC, you get the gain margin, GM. If you have the GM greater than 1, then the process is stable. So this is based on the gain margin criteria. And the phase margin, we have another frequency, WG, crossover frequency at which AR equal to 1. Remember that WC happen at angle negative 180. WG happen at AR equal to 1. This is the difference. WC happen at angle negative 180. WG happen at angle amplitude ratio equal to 1. The phase margin is defined by this. PM stand for the phase margin equal to 180 plus the angle at WG. So according to the criterion, the phase margin must be greater than 0 in order to ensure the stability of the closed loop system. So GM equal greater than 1, then this one PM must be greater than 0. So, and then, okay, that one is based on the stability. And then here we have the well-designed FB control system. Sometimes we can have the stable system by using the controller parameter. But can we have the good value of controller parameter? How to know? We use this rule of thumb. Although the GM greater than 1, it becomes stable, but the gain margin must be between 1.7 to 2.0 in order to make sure your controller parameter is good. That means your controller is well designed. No need to do the retuning. It must satisfy both gain margin and phase margin. Gain margin set between 1.7 and 2.0, and the phase margin must be between 30 degree and 45 degree. Okay, let's take a look on the AR and the phase angle. So here, when we start at negative 180, we draw the line until it reach the phase angle line. So this is WC. If we move the line up to the AR, then still this one is the same WC. Because the WC happened at negative 180. So negative 180, you reach the WC, then move to the AR line, and then you get your ARC, where the GM equal to 1 over ARC. That is the formula. So from here, we can get the value of the gain margin. For the phase angle, it starts at AR equal to 1. AR equal to 1, draw the line until it reaches here. Then you can have the WG, gain crossover frequency. So based on the WG, go downwards until it reaches the next line of the phase angle. On the left, here you have the angle. It's not WG here, it's the angle, Phi1. The WG is on the x-axis. So, this is what we call it the phase margin. Between the negative 180 and the W is your phase margin. So in this case, first you need to check the stability. The GM must be greater than 1 in order to have a stable response. And then the PM must be greater than 0 for the system to be stable. This criteria for stability. If we want to know the controller parameter is good or not, is well designed or not, you must follow this rule of thumb. 1.7 up to 2. And in the textbook is located 4. So change it to 4. 1.7 to 4. So this means if your gain margin between 1.7 and 4 and the phase margin between 30 and 45 degree, that indicate your controller is not only stable but also a well-designed feedback control system. So let's say you've satisfied the stability. Gain margin okay, greater than 1. Phase margin 0. But your gain margin and phase margin outside this range of well-designed control system. Let's say, for example, to make it clear, you have the GM equal to 1.2, phase margin equal to 10. So 1.2 and 10 is satisfy the stability. So that means your process is stable, but based on the rule of thumb well-designed feedback control, this one is outside the range of the well-designed gain margin. The 10 is outside the range. So meaning that your process your closed loop system is stable, but your controller is not well designed. What you should do to improve it? Then we need to retune our controller. Retune means we need to calculate new controller parameter for our controller. Let's say you use the KC, we calculate the new KC. How to calculate? We use what we call it Ziegler-Nichols tuning method. In this case, we require the information of the KCU and PU. The KCU can be obtained by equal to 1 divided by ARC. Maximum value of KC that result in a stable closed loop system. So we need to find our ARC, then we can find our KCU. And then for the PU stands for the ultimate period. The formula is 2 pi over WCO. WCO is the critical frequency. So once we find the KCU and PU, then we can substitute either using Ziegler-Nichols method or Tyrus-Lieben method. Only for the Ziegler-Nichols method, it is applicable for the P, PI, PID. Tyrus-Lieben only for the PI, PID. It is not working for the P controller. So this means if the question asks you to find the P controller parameter for the frequency response, automatically you use Ziegler-Nichols because you have the formula for the P. So in this case, once you find the KCU, you substitute the value of KCU inside the equation, then you can calculate the KC. By using the PU, you can calculate the tau I and the tau D. So this is the method to calculate new controller parameter. New controller parameter means the new value of the KC, tau I or tau D. In the previous example, the tuning method, you have direct synthesis, internal model control, integral time weighted absolute error, ITAE. That one is for the for the combined with the feedback closed loop system. This one specifically for the frequency response. Don't mix up. When you have the frequency response, you need to use this formula because here, if you take a look, KCU based on the AR, amplitude ratio defined at WC. WC is your critical frequency. Same goes with the ultimate period, WCO, you get at angle negative 180. So this is the method to find new controller parameter for closed loop system in the case for the frequency response. So let's say you calculate the new controller parameter. What are you going to do next? We repeat the step. We find the replot the Bode diagram again. Get the new Bode diagram. Get the new gain margin and phase margin, and check it meet the stability or not. And then we check either it is now fall inside the region of well-designed phase margin and gain margin. 1.7 to 4.0 for gain margin and 30 to 45 for phase margin. If not satisfied again, then that means you need to find another method. Maybe try Tyrus and Lieben, for example. You need to try until you get the range. Although if you keep trying it's not working again, then that means both method cannot be used, since it will contribute to the out of design control system. So that is the chapter 4 topics where you need to consider the frequency response, how from the transfer function will be converted into the frequency response for amplitude ratio and the phase angle. Once you get the expression for phase angle and amplitude ratio, you will plot the Bode diagram. From the Bode diagram, you will assess the Bode stability criterion, stable or not. Or you can use the gain and phase margin. Check the stability. If it's stable, then you check the well tuned controller. Is it your controller well designed or not, or well tuned? You check the range. If it's okay, then you stop. If it's not okay, then you will find new controller parameter using Ziegler-Nichols or Titus-Lieben. That is the overall procedure for the frequency response. Okay, in order to ensure a clear understanding, I will provide the tutorial. This will be included later. I will demonstrate first how we can assess the stability using the frequency response. So do not panic, do not be worried. Try to understand this one first. Please understand the criteria. Then we will perform the demonstration on how we can solve the problem regarding frequency response. That will be continued in the next online video. So with that, thank you very much for your attention. If you found any kind of mistake, please inform directly to me in order for me to improve the mistake. So that's all. Thank you for your attention again. Have a nice weekend.